Emma, before Christmas, we were looking at special relativity. Does anybody remember what made special relativity special? What did I say the acceleration had to be for all of the stuff we were looking at in that little Einstein special relativity unit? Zero. It's because acceleration is special. You're going to notice, probably more than any other topic, you'll find, especially if you take Physics 12, a bunch of different ways to calculate acceleration. It means a lot. We already have A equals VF minus VI over T. I think I rewrote that one correctly. We already have A equals VF squared minus VI squared all over 2D. That was the other one. And we have F equals MA. Next to this, can you get the A by itself? This was Brian's equation. Since Brian's back, we'll do it. Brian, what's another way to calculate acceleration? So if I know the force and I want to find the acceleration, just divide by the mass. Okay. We already can solve some fairly interesting stuff just with our knowledge of Newton's laws and that equation, which was Newton's second, F equals ma, A equals F over m. Sometimes you'll be asked to find a mass too, but not very often. What you looking for? They're all in boxes right there, I think. Sorry, I didn't put them all back on the cart. A spacecraft has a mass of that. It's in scientific notation because spacecraft are heavy. Its engine can exert a thrust force of that. Okay. What's this asking me to find, Brian? Part A. So here, I would say they gave me a mass of 3.25 times 10 to the fourth. They gave me a force of 7.25 times 10 to the fourth. I did a quick check. It's kilograms and it's newtons, which are the preferred units, so I don't have to do any unit conversions. I can go straight to your equation. This is not today's lesson. This is kind of a review of what we've done so far already. We can still use Mr. Dueck's DFIC approach. There is an equation that has F and M and A in it. It's F equals MA, and I can rewrite that one to get the A by itself. We did on the previous line. So it's going to be 7.25 times 10 to the fourth divided by 3.25 times 10 to the fourth. You want to get comfortable with scientific notation during this unit. So you want to know how to find scientific notation on your calculator during this unit. For me, 7.25 scientific notation button 4 divided by 3.25 scientific. And I know if I use my scientific notation button as well, I don't need to put brackets around the top and the bottom because my software knows those are one number and one number. It's a bit of an advantage. That's why I'm pushing you to get good at your scientific notation button. It's less typing. And I get 2.23. Yes? Anybody else? Is that a big acceleration? How big is 1g? How big is 1g? 9.8. So this is about a quarter of it. That you'd notice it, but it wouldn't be like, whoa, okay, we're accelerating. You know what? You probably pull about that if you're in a car and someone steps on the gas fairly, not flooring it, but not going nice and easy, medium. Is that okay, Christy? And it's an acceleration, meters per second squared. Suppose the spacecraft maintains this acceleration for 240 seconds before shutting off the engine. And it starts out with an initial velocity of 5.6 times 10 to the third. What will the final velocity be? Maggie, what's this question asking me to find? Okay, we can again use our from the beginning of the year before Christmas approach, so we can say, VF equals? We just found acceleration, so I'll drop it down. What's that 5.6 times 10 to the 3? Yep. What's that 240? Help me out. Did you memorize that? Because you're lazy and you got sick of looking it up, which is the only reason you should memorize it. You don't have to. It's on your green sheet, but I love the fact that you pulled. And we already have the VF by itself. So it's going to be 5.6 times 10 to the 3 plus 2.23 times 240. 5.6, scientific notation button, 3 plus 2.23 times 2. Oh, you know what? I'm not going to use 2.23. I'm going to use my answer button because that's going to be more accurate. Times 240. And I get 6135. I'll write it in scientific notation, 6.14 times 10 to the 3 meters per second, but I've got this stored on my calculator. Tristan, what's C asking me to find? Which variable? Yep. I'm not going to relist all my data because it's on the previous line. I think it's all the same situation. So I'm looking for an equation that's got a D in it and some other stuff. Sure, help me out. Which one you got? I'd go with that one. I could also use D equals VF squared minus VI squared all over. You know what? Let's use the one that's got the D by itself and no brackets because it's easier to type. I would go with that same one. Good. So I'm going to go D equals VIT plus a half AT squared, where VI was 5.6 times 10 to the 3. T was 240 plus 0.5, 2.23, 240 squared. 5.6 scientific notation button, 3 times 240 plus a half mv squared. I typed that in right? I think so. Do you get 148,224? 140,8224? See, you got that too? Okay. I'm going to write this one in scientific notation. 1.41 times 10 to what? 1, 2, 3, 4, 5, 6? Yes? 1.41 times 10. 1.41 times 10 to the 6th meters. $1.4 million meters. That's moving. Well, it's moving pretty fast. That seems right to me. D. What will the velocity of the spacecraft be after 480 seconds, or 600 seconds, or 1,000 seconds? And I'll give you a hint. It's a trick question. So all of you right now in B, underline that phrase there. When you're in outer space and you shut off your engine, what happens? What law is that? Newton's first. So what was our V final in B? In B? Our V final? V is going to stay 6.14 times 10 to the third until something else exerts a force on it. But since the engine is shut off, Christy, there's no force acting on the rocket. If it's in outer space, it's not being pulled by any planets. It's going to keep going in a straight line at a steady speed. And that works. It's how we got the Voyager satellites, which left well before you were born. They left in, I think, 79 is when we launched them from the Earth. One of them has now left the solar system, and it's going to keep drifting forever. Unless, by some fluke, its path takes it into the gravitational field of a star or a planet or a black hole, then it'll get sucked in and eventually crash. But for now, it's going to keep going in a straight line at a steady speed. Newton's first. Is that okay? It's not what I wanted to talk about. That was to jog our memory. I want to talk to you today about what's called a free body diagram, which I usually abbreviate as an FBD. Perhaps, Cole, the single most useful tool I'm going to give you all year. A free body diagram is a picture where you represent the object that you're analyzing with a dot. Any forces that are acting on the object are represented with arrows, roughly to scale. What I mean by roughly to scale, if, Misha, you know that force A is bigger than force B, draw arrow A bigger than arrow B. If you know that force B is smaller than force A, draw arrow B smaller than arrow A. That's what I mean by roughly to scale. Oh, if you know two forces are identical, Chloe, try and draw the arrows about the same length. Eyeball it, but certainly don't do one arrow that long and one arrow that long and tell me those two forces are equal. I'd glare at you. And we're going to use Newton's laws to figure out other forces that are acting on the object. For example, free body diagrams for four situations are shown below. The net force is known for each situation, but some of the forces, the individual forces, are missing. We don't know them. We're going to analyze each situation and determine the magnitude of the unknown forces. Here's what I mean. Hannah, this first diagram, what's the net force? You know what that means? Newton's first law says if your net force is 0, all of your forces have to be, I'm looking forward, begins letter B. Okay. How big must B be? Can't be 0. What? Has to be. If I got 200 down, I know there must be 200 up. If there was not, I would be accelerating. The force would not be 0. Hannah, how big must force A be? You okay with that? Nick, what's the net force in the second diagram here?
900 up.
So how big must force C be? 11. Yes! Good. Dylan, what's the net force in this diagram? So, how big must force D be? Yes. How big must force E be? Has to be, otherwise there would be a force up and down. This is the power of Newton's first law. Newton's first law lets you figure out missing forces. Jacqueline, how big must force G be? Yep. Now let's see how good you are. You ready? How big must force F be? Exactly how big? Can anybody see it? Think algebra and variables. How big must force F be? Exactly how big? Look at your diagram. What? I heard someone say it. Oh, I thought I did. What must it be the same size as? Is there any vertical force? So how big must force F be? You don't need numbers. Here's what I do know. They have to cancel. What that would mean is if you told me how big H was, I would know how big F was. If you told me how big F was, I would know how big H was. But for now, I can tell you the same. A book is at rest on a tabletop. All of your binders. What would the free body diagram look like? So here is our first free body diagram. We represent the mass with a dot, like that. And then I walk through a certain procedure. So if you look at your binder, I always say, what are the forces acting on it? Get the obvious one. And the obvious one is the fact that we're sitting on the Earth's surface. What holds all of us on the Earth's surface? Gravity. So I draw an arrow pointing down, and I call it FG, force of gravity. Is your binder sinking into your desk like quicksand? Is it flying into the air like Superman? Is it accelerating? Then the forces must be, I'm looking forward to begins letter B, balanced. So there has to be an arrow the same length that you drew gravity. There has to be an arrow that same length pointing up. There has to be. What's that? What force is that? What's keeping the book from sinking down onto the ground? It's so obvious that it's tough. That's the free body diagram on your binder. Gravity's pulling it down, the desk is pushing it up, and I know they're the same size because if they weren't the same size, Emma, your book would have to be accelerating, and it's not. Okay. Example 2 says, draw a free body diagram for the following masses hanging from a rope. So, I'm going to represent the mass with a dot. What are the forces acting on it? Get the obvious one. What did I say the obvious one was if you're near the Earth? So let's draw gravity down. Is this mass accelerating? No. So that means the forces have to be, I'm looking for a word that begins with letter B, balanced. So I'm going to draw an identical length arrow pointing up. And what I mean by identical length here is eyeball it. I would be frowny if you did this. I would be frowny if you did this. Eyeball it. So for me, what force is that? What's keeping it from falling? What's the mass hanging on? We give the force from a rope a special name. We're going to call it tension, and we're using a capital letter T. Any cable, any cord, any rope exerts tension. What's the difference between this diagram and this one here? Well, here is the mass. What are the forces acting on it? Get the obvious one. Gravity down. And now, are you ready? Which way is this mass accelerating according to this question? I'm going to ask you the same question. I want the same answer. I'm just going to phrase the question differently. Which way must there be a bigger arrow pointing? Has to be. I tend to exaggerate it so it really stands out, so it catches my eye. What force is that? Yep. In these two diagrams, which of these ropes is more likely to break? The second one, because you're requiring more of tension. Turn the page. We're going to learn different types of forces. One of the forces that you're most acquainted with is the force of gravity. This is the force that the Earth's mass exerts upon you. It sucks you down onto the Earth. The force of gravity is calculated as follows. F equals what? F equals what? This is Newton's second law. Remember the equation? F equals ma. What's the acceleration due to gravity? What's the A of gravity? 9.8. We have a special symbol for that. The force, yes, Cole just whispered it. The force of gravity is that. Where G is 9.8 meters per second squared. I'm going to ditch the negative in this unit because we're often going to let down be positive because it makes the math easier. So, and we're more concerned with magnitude. In fact, from now on in a free body diagram, instead of writing FG, you're going to see I just write the actual formula or equation mg. You don't need to go back and change it, but from now on, you're going to see me whenever I say get the obvious one, I'm going to put mg. That's the force down. Until we go to outer space, but outer space will be next year. There's another word for the force of gravity. Weight. Weight is a unit of force, not mass. It's measured in newtons, not kilograms. If you tell me that something weighs 38 kilograms, I'm going to glare at you and I'm going to say, no, it doesn't. It has a mass of 38 kilograms. If you want its weight, you better multiply that by 9.8, and that will be its weight in newtons. The force of gravity upon you is called what? What's another word for the force of gravity upon you? No now. No now. Wait, no now. Wait, no now. It's a joke. It's a funny. She didn't. Okay, whatever. So, example 3, and I will be fussy on the difference. I will ask you on tests for weight, and if you give me an answer in kilograms, you're losing marks. Okay? Find the weight of a 35 kilogram object on the Earth and on the Moon where g is smaller. Mateo, not Mateo, but Mateo. What does this question want me to find? No now. What does this question want me to find? Okay. So I'm going to do A. I'm going to do B. How do I calculate weight? Weight is the force of gravity, and it's calculated by mg. Except g varies from planet to planet. So I'm going to put, for part A, g Earth. For part B, I'm going to put g Moon. What's the mass of this object, Mateo? What's g on the Earth? So this will have a weight of 35 times 9.8. It's going to be 350. Take away 7. Is it 343? Double check me. Yeah? 343 newtons. That same object will have the same mass on the Moon. Your mass doesn't change. It's the same everywhere in the universe. What changes based on your location is your weight, because it depends on what planet you're nearby. So this is going to end up being 35. What's g on the Moon, Mateo? 35 times 1.6 is going to be 350 plus 21. Is it 371? No. No, I'm wrong. 300. What is it? No, sorry. I'm way off. It's got to be smaller than 343. I forgot to carry a 1. It's going to be 35. Oh, 56 even. Yeah. Yes. I totally carried a 0 when there wasn't one. This is why objects feel lighter on the Moon. Has their mass changed? No. What has changed? Force of gravity. Okay. Near a black hole, this number here approaches infinity. That's why it's so tough to get out of a black hole. Not because your mass changed, but because the gravitational field strength, the acceleration due to gravity, changes. That varies from planet to planet to planet. Here is the theme of today, solving force equations. And here is the key. You can put a little star next to this if you want to. To solve force equations, we're going to use a tug-of-war analogy. We're going to draw an FBD. What does FBD stand for? We're going to draw a free body diagram. We're going to carefully label all the forces. We're going to use our knowledge of physics to figure out any missing forces. And then we're also going to use our knowledge of the situation to figure out which force is the winning, the strongest, the biggest force. Which way is it accelerating? That's which way the biggest force is. We're going to use the following equation then. We're going to say winner minus loser equals F net. Equals the net force. Where F net, where the net force is just equal to MA. So we're really going to go winner minus loser equals MA. And what this means, Maggie, is sometimes we're going to let down be the winner because it makes the math easier and more convenient, and that's okay. So we don't need to put a negative in for the 9.8s during this unit anymore. We'll take care of that in our setup of the equation. Let's look at an example. I'd like you to imagine a box is resting on ice, and you know the following forces are acting on it. A says, add any forces that you think are missing. You know what this is a job for? A free body diagram. I'm going to do the free body diagram right here. There's the box. Now, they already told me that I have 14 newtons that way, and I have 6 newtons that way. Imagine that you're looking at a box sitting on some ice. What are the forces acting on it? Get the obvious one. So I have mg down. Is the box sinking into the ice like quicksand? Is it flying into the air like Superman? So what can you tell me vertically the forces have to be? I'm looking for a word that begins with the letter B. So I know there's a force. I'm going to draw it the same size as mg. What force is that? Well, that's the ice pushing back up. Because if the ice wasn't there, the box would fall. So A says add any forces you think are missing. Emma, those are the 2 missing forces that have to be there. How do I know there's 2? I know gravity's there because we're on the Earth. And because we're not sinking into the ground like quicksand or flying into it like Superman, because we're not accelerating, I know the forces must be balanced so that the net force is 0. That's the power of Newton's first. Vertically, Emma, everything is balanced, so who cares? Is everything balanced horizontal? Who's winning? More specific in this question. So here is how we're going to solve this. We're going to use, I'm going to write this once and then we'll stop. Let's write capital W minus capital L equals F net. Winner minus loser equals F net. We're going to skip that step and we're going to go straight to plugging in forces. Which force is the winning force? More specific exactly? Minus. Which force is the losing force exactly? Whoop. And what did I say winner minus loser always equals? More specific, what did I say F net always equals? Yep. What did B want me to find? How would I get the A by itself, folks? How will I get the A by itself? Brian's method, divide by M. This is why I can't give you a one-size-fits-all equation. It's going to be, I don't know what forces are acting on the object. This is a job for a free body diagram. And then winner minus loser will be the template that you can use to derive your specific equation for your specific situation. But I can't come up with every single one that's out there. What'd you say, divide by M? I'm going to go like this. Dunk. Dump. Here we go. A equals, in your head, Emma, 14 take away 6. Yep. Divided by, what was M from the picture? Oh, sorry, I couldn't hear. Yep. 9 divided by 3 is 3. 8 divided by 3. Is it 2.6 repeating? Double check me. Yeah. So 2.67. Okay. There's the magnitude. If they wanted a direction, which way must this thing be accelerating? What does Newton's first law say? It has to be accelerating in which direction? To the right. Why? Because that's which way my unbalanced force is. How far am I going to get today? I got lots of examples. We're not going to get anywhere near through all of this today, I don't think, but let's see. I like example 6. I like example 6. Example 6 is the next question. Joel, what does example 6 want me to find? Find the, like you're feeling right now. tension, feeling, nothing, okay. You know what this is a job for, Joel? This is a job for a free body diagram. You know what this is a job for, Joel? Let's represent the mass with a dot. Right there. What are the forces acting on this 12 kilogram mass, Joel? Get the obvious one. What are the forces acting on it? Get the obvious one. I'm not looking at the by the way, that 2 is an acceleration, not a force, because it's meters per second squared. When I say get the obvious one, which one am I saying? Go systematic. I'm going to teach you to go systematic on purpose. Which is the first force I'm going to fill in? Help me out, folks. Gravity. Which way? Okay, so I'm going to go like this. Get the obvious one. Gravity. And what was the equation for the force of gravity? mg, where g was 9.8. What else? Look at the picture, Joel. Which way is this thing accelerating? I'm going to ask you the same question. I want the same answer. I'm just going to phrase it differently. Which way must there be a bigger arrow pointing? I'll exaggerate it so it catches my eye. What force is that? It's the rope. What do we call the force from the rope? I'll give you a hint. It's what we're being asked to find. Yep. Those are the only 2 forces acting on it. That 2 is an acceleration. It's not going to show up on my free body diagram. Those are the forces acting on it. Which way is it accelerating? Who's winning? Which way is it accelerating? Which force must be winning then? Here's my equation. So now you've just decided up is winner. My equation is going to look like this. Tension, winner, minus, who's the loser? Oh, that came out wrong. Well, that brought back bad memories of bullying on the playground, Mr. Dewick. Who's the losing force? Equals, what does winner minus loser always equal? F net, and F net is always equal to MA. Here's our equation. Don't memorize it, not worth it. It'll change depending on different situations. Memorize the winner minus loser approach in the free body diagram. What did you say they're asking me to find? How would I get the T by itself? Well, there's a minus mg. How would I move that minus mg over to the other side? Loud and proud. Yep. You see why I said I can't give you one-size-fits-all equation. You have to derive it yourself, but we can get there. We're going to practice this. So you're telling me, and you're right, that it's going to be MA plus MG? Now it's plug and chug. What was the mass, Joel? What was the mass of this particular one? Look at the picture. Yes. What was A? Yes. You said M was 12. What was G? We don't care about the negative. We've taken care of that. We just need the magnitude. How big is G? You know this one. No, G. This thing. No? Yeah, there, Captain. By the way, I'm glad you did that. Oh, yeah, that was a Captain Obvious mistake. We fixed that. Okay. What's the tension in this rope? Whatever that works out to be. It's going to be 24 plus 120 plus... It's going to... oh, heck. Oh, I should be able to do it in my head. It's 12 times 11.8. So it's going to be 12 times 11, which is going to be 132 plus another 12. 144... Is it 141.6? Or am I way off? I'm on? 141.6. And I'll call that 142. I'll go to 3 sig. Really, I should go to 2 sig figs, but whatever. Units. Tension is a force. What are the units for force? Newtons. You okay with that, Joel? So I have to emphasize, Tristan, I cannot give you a DFIC one-size-fits-all, list your data, here's the equation, approach. What I can say is, this is a job for a free body diagram, list your forces, Figure out who's winning based on the diagram or based on your knowledge of the situation, and then use winner minus loser equals MA. A couple more, we're going to pause. David, what does example 7 want me to find? You know what this is a job for? Joel, you know what this is a job for? David, you know what this is a job for? Now, how do I know? I see accelerations and there's multiple forces and they're wanting me to find a force. I'm going to pull out a free body diagram here. I'm going to represent the mass with a dot right here on the left since I have some room there. What are the forces acting on this mass, David? Get the obvious one. What do I mean whenever I say get the obvious one? Because it's meant to be obvious. Which way? Okay. No, 9.8 is the acceleration. mg is the force of gravity, not 9.8, m times 9.8, but get in the habit of just putting an mg there. That way when we go to other planets, you just have to adjust the g value, but not the actual diagram. Okay? Which way is this object accelerating according to this picture? Which way is the winning biggest arrow pointing according to this picture? So, is there a force up? Yeah. How do I know there's a force up? If there was no force up, what would A be instead of 4.2? If there was no force acting up, what would A be? It would be 9.8. So if they gave me a 9.8, I would say, ha, there is no force up, and I would just move on. But is it 9.8? It's less than. There must be a force acting up. What force is that? It's the rope. What do we call the force from the rope? And I'm going to draw it shorter. I'm going to exaggerate it so it catches my eye because I know gravity's winning because down is winning. Let's get an equation. Who's winning? Good. Who's losing? What does that always equal? F net, which is just going to be, yes. Good. What are we trying to find? What are we trying to find? Read the question. Find the... Don't overcomplicate it. I'm not going to try... By the way, you may have noticed in physics, I'm not trying to trick you as to what we're being asked to find. It's usually pretty obvious. So what are we trying to find? I want to get the t by itself. What's right in front of the t that I don't like very much? So I'm going to do something, I always call this the swappy dance. Here's what I mean. Look up. I'm going to plus the t to that side, draw a little arrow like that. At the same time, I'm going to minus the ma to this side. That would get the t by itself. What's going to drop down like a domino? The mg. And then I'll have a minus ma. That equals the tension. Is that okay, Mateo? You don't have to do it that way, but if you do that and you get comfy with it, it gets rid of a negative in front of the t and makes the equation much, much prettier. Now we're at the plug and chug stage. What was the mass, David? G? Yep. And not negative. I took care of that in my winner minus loser approach. In fact, in this case, we let down be positive because it made the math easier. Minus, you said the mass was 12. What was A?
4.2.
What's the tension? (12 times 9.8) take away 12 times 4.2, 12.4.2, 12 times 4.2. You get 67.2. Units, it's a force. What do I measure force in? Newtons, good. Hey, when is a rope more likely to break? When you're trying to accelerate something up or when you're trying to accelerate something down? When is a rope more likely to break? When you're trying to accelerate something up, or when you're trying to accelerate something down? Sierra? Convince me. She said up. Convince me. First of all, if we're talking about the force in the rope, what do we call the force in the rope? Okay. I have two equations for tension. Look, 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 look. On the way up, tension is calculated by going gravity plus ma. On the way down, tension is calculated by going gravity minus ma. What's going to give you a bigger force of tension? Plussing something onto gravity or minusing something from gravity? Plussing. This is always going to be smaller. Lowering it down is going to reduce tension. Accelerating it up has to increase tension. Has to. We'll finish with example 9 and we'll hit pause. Example 8 and example 9. Find the tension in the rope if the mass is moving up at a constant speed of 3.8 meters per second. Gotcha. Okay. Mike, what's this question asked me to find? You know what this is a job for? Good. Let's represent the mass with a dot. What are the forces acting on this mass? Get the obvious one. I agree. Which way? Good. What else? How do I know there has to be another force? If there wasn't, this would be accelerating at 9.8. It would be in free fall. And I've read the question. It's not. So is there another force? Yes. Which way? Bigger, smaller, or the same size as tension? Which way is this mass moving? Up? Okay. So you might be tempted to make a mistake. You might be tempted to do this and say tension was bigger. Go ahead. Make tension bigger. We're wrong, but make tension bigger. Who's winning? And from my diagram, who's losing? What does that equal? MA. And then you might say, I'm going to get tension by itself. How would you get tension by itself? How would you move that minus mg over? So you get this, mg plus ma, or ma plus mg. Does anybody spot, there was a phrase that I should have underlined or that should have stood out to me in the original question. What's the phrase that I should have caught? Constant what? Everybody right now, underline constant speed. What does that mean? What's zero? So you're telling me that there is zero? What's m times 0? So you're telling me that tension equals mg? You know what? There is no winner or loser. It's a tie. If I was drawing this free body diagram correctly, my tension arrow should have been the same size as mg. And I would just correct it like that, and I'd figure out what you made. But I did it wrong on purpose to let you know, Christy, as long as you're paying attention in your final steps, you can often catch sloppy mistakes. Because I think every one of you would have said 3.8, wait a minute, that can't be an acceleration, because what are the units? And what's the units for acceleration? Has your teacher mentioned that it's worth memorizing? It is worth memorizing units, by the way. And constant speed. I'm hoping most of you somewhere here would have said, it can't be accelerating, which means forces must be balanced. If you caught it on the first line before going anywhere, yay, that's what I would do. I would have noticed, winner equals loser because we're not accelerating. But even if you don't, there's multiple places along the way, Emma, to not be confused, to say, hey, this looks weird. Oh, it's not accelerating. I can make the correction. Is that all right? And let's get an answer. What's the mass? G, 9.8. 12 times 9.8, it's going to be 130. Take away 2.4, it's going to be 127.6? Or am I wrong? Sorry? 117 points. Yes, 117.6. I carried a 1. Gosh. I'll call it 118. I'll go to 3 sig figs. Units, Michael, it's a force. Yes. Not only can I give you the acceleration and say find the tension, as far as I'm concerned, I can give you the tension and say find the acceleration, Emily. So number 9 says, suppose the chord tension is measured at 98 newtons. What's the acceleration of the mass? What does this question want me to find, Emily? You know what this is a job for? Let's represent the mass with a dot. What are the forces acting on this mass? Get the obvious one. What else? There must be, because it says, suppose the chord tension is. Which way? Up. Bigger, smaller, or the same size as mg? I don't know. How big is tension? They told me. You know what? On your calculator, get your calculator out right now. Calculate mg really quickly. Can you go, what's m? Go 12 times 9.8, just on in the margin. Or heck, you don't even need to write it down. On your calculator, how big is mg in newtons? 117.6. How big is tension in newtons? How big is mg? 117.6. How big is tension? Who's winning? Gotta be. I'm going to draw tension shorter. See, I was able to reason my way there with a tiny bit of calculator help. I've gone on my rant about getting a good calculator. Yes? Okay. Now I can generate my equation. Who's winning? Who's losing? What is that going to equal? No. What's winner minus loser always equal? MA. And now we pause and we say, what's this question asking me to find? What does this question ask me to find? Oh. Brian, how would I get the A by itself? And this is one of the many reasons I showed you formula manipulation, so you don't have to try and memorize yet another equation, so you can look at any equation and get whatever you need to by itself without trying to rewrite them all. So you say, if I want to write this in a line, you're telling me it's going to be mg minus tension divided by m. Emily, do you mind? I'm going to put the A equals on that side, because that way I have the A kind of by itself where I like to see it. Okay. What's m? 12. G, 9.8 minus T, 98. What's m? 12. Emily, is this a fraction? Is there more than one thing on the top? What am I going to have to remember around the top? Brackets. Is there more than one thing on the bottom? Then practice typing this in. And I get this thing must be accelerating at 1.63333. I'll go 1.63. Direction, who was winning? Down, if they asked for a direction. Units for acceleration? Yep. You're going to find often I won't ask for a direction in this unit. I'll just want the magnitude. But if I asked for it clearly here, down. How do I know? Gravity had to be winning. How do I know? I calculated it and it was bigger than tension. Homework that you can start with. You can try number 1 as kind of a head start if you want. But I'm going to say put your pencils down, look up.